Okay, welcome to week one, part one of the EDA and Viz course. We're going to take a look in this lecture at things that you should already know from a prerequisite course. Some fundamentals of Python and also information about NumPy. So, in Python, we can run a shell, and the shell will then execute Python statements that we type to the shell. Now, for lecture purposes, I like to use idle because the shell that idle displays is extremely plain. There are no special windows, no slider bars, no menus, no icons all over the place. It's just very plain interface. The three greater than symbols here are the prompt, and at the prompt I can type commands, Python code statements such as a gets 123. And then if I type a again, that displays the value that the variable a is currently referring to. Now, throughout this course, you should please make use of a Jupyter notebook or multiple Jupyter notebooks for the various homework assignments and your group project, because future courses that you will take that have this course as a prerequisite will assume that you know how to use Jupyter notebooks. But I find Jupyter notebooks are just too busy and messy for lecture purposes. Okay. Now, a variable, such as I created here, this variable a, is simply a reference to some kind of object. The variable itself does not have a data type associated with it. If I say something like I gets 123, now I've created a variable I, currently referring to an int variable, an int value 123. I can ask for the type of I. I'm not actually getting the type of the variable itself here. What I'm getting is the data type of the object that I is referring to. And I'm told that I is referring to an int object currently. But I can modify I by saying I gets 2.7. Now the variable is referring to a floating point value. And if I ask for the type of I now, I get told that I is now referring to a float. Okay, so this is unlike other more traditional languages like Java and C++, where the variables themselves have data types associated with them. In Python, a variable is merely a reference, and it is the object that the variable refers to that has a data type. If I say I gets hi, now I is referring to a stir, and the type of I is stir or string. The low-level data types that we're going to be making use of in this course are the int data type, which is arbitrary precision. That is, you can have integer values that grow as big as you want, either in the positive or negative direction, basically up to the limit of how much memory you have on your machine. The float data type is equivalent in format and layout and size to double values in a Java or C++ kind of environment. That is, they occupy 64 bits of memory. They are able to store floating point values out to around 15 or 16 digits of precision, and they have a range of exponents roughly in the vicinity of plus or minus 1024. 10 to the 1024 power, 10 to the minus 1024 power. A stir is able to hold a any Unicode UTF-8 value. And for our purposes in the US, we are using a very limited subset of that, the so-called ASCII character set. And the ASCII character set only requires 1 byte or 8 bits of storage for each character. Actually, technically only 7 bits for the 7-bit ASCII character set. We're not going to worry about binary data in this class, so I'm not going to bother needing you to know about bytes. Bool values, that is Boolean values, can be either true or false with a capital T or F. And then we have the special value none, which is the empty value, the null value, the value the value that indicates no value. Okay. I am, by the way, intentionally flying through this material because, as I said, you're supposed to already know all of this stuff. If you have questions about it, and if you are not confident that you know these things, send me an email message and I can refer you to more relaxed and more detailed lectures covering the same material but in more depth and at a slightly slower pace. Here are the entire collection of arithmetic operators that are available to you in Python. This table shows them in order from highest precedence for exponentiation down to lowest precedence for the binary plus and minus or addition and subtraction operators. There are also unary versions of plus and minus that are just stuck in front of values to indicate a positive or a negative value. And then we also have the so-called multiplicative operators. Multiply, regular division, floor division, and modulus. Now, most of these binary operators associate from left to right, but exponentiation is an oddball here. It associates from right to left. And so you need to be careful to remember these rules. Division always produces a float. So if I ask for 22 divided by 7, even though 22 and 7 are both ints, and in Java or C++, this would be an integer division that truncates the fraction, yielding exactly 3. In Python, we get a floating point result. And this is a not very great approximation of pi. Even dividing by 1 produces a float result. All right, so 5 divided by 1, which looks like you're not doing anything, in fact, gives you a floating point result, 5.0. Now, here I'm doing exponentiation, 1 to the 1 power. Both of these operands are integers, and the result is an integer. But if the exponent is negative, here I'm doing 1 to the power of minus 1, a negative exponent implies that we're doing division. 1 to the minus 1 power is actually 1 over 1. There's an implicit division going on there, and so we get a result of 1.0 from that. Strings can be written either in double quotes, or in single quotes. You can use a plus sign to concatenate strings together, and a star symbol, a times symbol, for repetition, right? So ASDF plus QWERTY, I get the concatenation ASDF QWERTY. If I ask for ASDF times 5, I get ASDF repeated 5 times in one longer string. I can use triple single quotes or triple double quotes as yet another couple of ways of defining a string literal. And one of the nice advantages of these two notations is that I can define a string that's multiple lines long. So if I say something like S gets quote, 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 this is a 4-line long example of a string in triple double quotes or triple single quotes. So now S, each place where I type the enter key, we'll see in the string S that a new line character represented by \n has been stored at that location in our string. The print function displays values in human readable form rather than in internal code representation form. And so if I say print S, I see 4 lines of output from printing that one string S. Each place where a new line character appears, print produces a carriage return and a line feed so that the next text comes out on the next line down. We can combine the various arithmetic operations with assignment to produce the so-called assignment operators. Now, I still have A sitting around containing 123. If I say A plus gets 2, that's the same thing as A gets A plus 2, and consequently A has been modified now to 125. So those are the low-level data types and arithmetic. Python provides a number of built-in collection data types as well that we can use to keep track of multiple values at the same time. A list is similar to an array in languages such as Java or C++. We can create a list, we can subscript into a list, we can modify items in a list, and so on. We'll look at lists first, and then we also have tuples, sets, and dictionaries, or the other three built-in collection types that Python provides. So to define a list interactively, or manually, I'm going to give a variable name. You usually want to have a variable name to keep track of any data that you create. So square bracket begins the definition of my list, and now I'm going to have in here values 7, 2, 3, and 0. I just type a sequence of values or a series of values separated with commas and a closing square bracket. So, whoops, I hit that backslash by mistake. All right, let me try again. So M now contains the 4 values, 7, 2, 3, and 0. I can subscript. Oh, let me point out that the data type of M is list in this case. And I can access individual items within the list by using integer subscripts. The integer subscripts start from 0 just as they do in Java, C, C++. So at least that's similar to other languages you probably already know or may have been exposed to. So M sub 0 is going to be the 7. M sub 1 is going to be the 2. M sub 3 is the last item in this list, which has a value of 0. If you attempt to go outside the bounds of the list, you get an error. So I have an index error attempting to go past that value 0. Another cool thing that you can do with lists is to count backwards. Item sub -1 is the final element in the list. Here's just a reminder of what our list contains. So m sub -1 is the 0, m sub -2 is the 3, m sub -4 is the 7 at the beginning of the list, and as we did with positive indexes, if I try to go back too far prior to the beginning of the list, I get an error. Okay? Now, you can modify items in a list. So this means that a list is what's called a mutable collection in Python. Many other collections are mutable. Some kinds of collections are immutable. That is, once you create these immutable collections, you're not allowed to change their contents. All right, so here's m. If I ask to change m sub 2 to a 5, that works fine. So m sub 2 is the 3 originally here, but I'm saying m sub 2, that slot gets the value 5, and that therefore changes that third item value, the sub 2 item value in the list. Just like we saw with strings, plus can be used for concatenating lists, and star or multiply can be used for repeating lists. Here's my list m. If I say m plus some other list, 471, let's say, I get a copy of m. That gets concatenated with 471, and the result is 7250471 as a list. Now, this didn't change m. All right, so m remains unaffected by that. If I want a list of 20 zeros, well, rather than counting out 20 zeros, I can just say, give me a list of 1 0 repeated 20 times. And now that gives me a list of 20 zeros. In these two cases, both where I showed the concatenation and where I showed the repetition, these lists were just created and displayed on the screen, but then they vanish because I didn't establish a variable to keep track of them. So let me say mz for m zeros, list of zeros, gets a list of 1 0 times 20, and there's our mz. I can use the len function, by the way, to find out how many items any given collection contains. So that confirms for me that mz contains 20 items. M itself contains 4. Having trouble typing. Okay, 4 items. And a string can also be thought of as a kind of collection. If I ask for the len of hello, each character counts as an item in that string, and so I get told that that's 5 total items. In addition to these two symbolic operations, plus for concatenation, times for repetition, the list data type also supports a variety of named operations. And let me just hastily show you some examples of these. I'll start with m, and we will modify m. So I can say m.append and give a value, and that puts that value at the end. I can, let's say, append a 2 as well. All right, so now I've appended a 9 followed by appending a 2. Insert is a little more complicated because I have to specify the index ahead of which I want to insert my value as the first argument, and then the second argument is the value that I want to insert. So if I want to put a value at the beginning of my list, I could say m.insert ahead of position sub 0, meaning ahead of the 7 that's currently at the beginning, and let's put a 0. Well, let's put a 5 there. Whoops. So we have now inserted a 5 ahead of the 7. I can use remove to remove any value that exists. If I say m.remove 9, that removes the very first 9 found in the list. There is actually only 1. So that 9 has now been removed. m.remove 2 eliminated this first one, but left the other one behind. Okay. Count will tell me how many times a value occurs. If I say m.count 5, I get told there are 2 5s. m.count 7, there's only 1 7. m.count of 13, there are 0 13s in the list. If I say m.sort, the items get sorted. Here in my slide it says ascending. Technically, this should be called non-descending, but non-descending wouldn't fit neatly on my slide. Non-descending allows for the possibility of duplicates. And so if I sort M in non-descending order, I'll have a 0 first, then a 2, then these 2 5s, and then the 7. And when I redisplay M now, I see that that did in fact occur. M.reverse will simply take whatever items exist within M and reverse their order. Okay, and these are similar examples. So that's lists. Now a tuple is another kind of collection type. To define a tuple, we use parenthesis characters instead of square brackets. So here I'm creating a tuple called n, and this tuple, just for a change of pace, I'm going to create here a tuple of a bunch of strings. You could have a list of strings or a list of floats or a list of mixed ints and floats and bools and various other things. My tuple is just going to contain strings. So I have as my first string, and then golden as my second string, and then eagle, and then soars. So I guess I was feeling literary and outdoorsy when I wrote this example. So n is now a tuple containing a golden eagle soars. Just as with a list, I can use square brackets to index within the tuple. I can go from 0 up to the length -1, or from -1 back down to -n. So n sub 0 is the string n sub 3 is soars, n sub 4 is out of bounds, n sub -1 is soars, n sub -3, let's say. Let's see, so -1 is soars, -2, -3 should be golden. And I can't go prior to the beginning of the tuple. N sub -5 gives me an error. All right. Now, a tuple is immutable as compared with a list, which was mutable. That means that a tuple cannot be directly modified. Here's my tuple, n. If I attempt to say n sub 1 gets bald, okay, my idea here is that instead of a golden eagle soars, I want to change that to a bald eagle soars. We don't actually have golden eagles this far east, but we do have bald eagles in Pennsylvania and elsewhere. in the northern part of the U.S. But this fails, okay? Tuple does not support item assignment, all right, because it is immutable. We're not allowed to do that. However, we can sort of fake it. We can simply reuse the variable n to refer to a different tuple defined using items from the original tuple. All right, so here's n, which means n sub 0 is n sub 2 is eagle, n sub 3 is soars. If I modify the variable n to refer to a new tuple consisting of n sub 0 followed by the string bald, followed by n sub 2 and n sub 3, well, this is a brand new tuple. It's not the same tuple as the original tuple n that I created previously. It is a brand new tuple, but it's defined using pieces from the original tuple named n, and I'm reusing the name n over again to refer to this new tuple. So technically speaking, I did not modify the original tuple that n was referring to, but I have modified the variable n now to refer to a totally different tuple, which was built using pieces of the original tuple n. So even though technically a tuple is immutable, you can sort of fake it by copying and pasting pieces of the tuple into a brand new tuple. Now, if you have a tuple, you can use a feature called sequence unpacking to take all of the values in the tuple and assign each of those values to different variables if you have the same number of variables as there are values in the tuple. Let me point out that len of n is the number of items in the tuple, which is 4. Therefore, if I type 4 variables on the left side of the assignment, A, B, C, D, separated with commas, and I say gets n, this is equivalent to saying, basically what we're doing here is we're saying A gets n sub 0, then B gets n sub 1, then C gets n sub 2, and finally D gets n sub 3. All right? So this statement, A comma B comma C comma D gets n, is essentially a shorthand for what I've typed in this comment. That is, A refers to the word B refers to bald, C to eagle, D to soars. It also turns out that you can build a tuple without bothering to use the parentheses around the values. And this is referred to as tuple packing. That is, here's my n. I could say, well, let me just use the example in the notes here. If I say T gets, and then I just type a sequence of values separated by commas, 1 for high and 4.6. Notice that these are not all the same data type. I have an int, another int, a stir, and a float. That's fine. Those simply get gathered up and turned into a tuple, and T refers to that tuple. All right, so I can do both sequence unpacking by assigning the contents of a tuple into multiple different variables, or I can do tuple packing by having a sequence of values separated by commas and assigning all of those into some variable that actually creates a tuple for that variable to refer to. You can perform what's called multiple assignment by combining the idea of tuple packing on the right side of the assignment with sequence unpacking on the left side. That is, if I said A, comma, B, comma, C, comma, D gets high 12.6, true 9, the values on the right side are simply stored or assigned to the corresponding variables on the left side, which is actually kind of hard to read, but it does work. So A refers to high, B refers to 12.6, etc. The one place where this idea of multiple assignment is used very routinely in Python is if you want to swap the values of two variables. Let's suppose that I have A referring to the value -7 and B referring to the value 3. If I say B comma A gets A comma B, this does a correct swap of those values. So what happens is that the values of these variables on the right side are obtained. So the value of A is -7. The value of B is 3. And then these two values, -7 and 3, are assigned into, or to be referred to by B and to be referred to by A, respectively. So when I now look at A, it's referring to 3. B is referring to -7. It's a handy trick to know. The third collection type we're going to look at is the set. And whereas we use square brackets to define a list, parentheses to define a tuple, we're going to use curly braces to define a set. Items in a set are stored in no particular order, and no duplicates are allowed to exist within a set. Now, to define a set, you just use curly braces, and then you give a series of values you want to put into the set. And notice when I do this example on the slide 20 here, I am using some duplicates, but it turns out that's okay. The duplicates just get ignored. So I'm going to say 1, 6, 5, 9, 2, 1, 6, 3. All right, well, if we scan through these values, 1 occurs twice, 6 occurs twice. I guess those are the only two that occur twice. So the extra 1 and the extra 6 over here basically just get tossed out. And S ends up containing just 6 values instead of 8. The data type of S is a set. I said that the values in a set are stored in no particular order, and that is true, although you may be fooled into thinking that they are actually sorted just because of the way that they are displayed on the screen. But as we progress through some examples, we will see that the values are in fact not stored in a sorted order. Now, a set is not subscriptable. If I say S sub 0, I get nothing. That's an error. Okay, a set object is not subscriptable. Basically, all we can know about things in a set are whether a particular value is in a set. I can ask whether 6 is in the set S, and that's true, or whether 7 is in the set S, and that's false. All right, so this is how I can determine whether a certain value is in the set, but I can't do subscripting. There are a variety of named methods that I can use for interacting with the set, including adding a value. Now, in the list, we had the concept of inserting ahead of an index or appending at the end of a list, but the set has no concept of a beginning or an end. So instead of insert or append, all we have for sets is add. And we can't specify where that value is going to be added because sets are not sorted. So if I say s.add, let's say a 12. Okay, 12 has been added. If I say s.add 3, 3 is already in there, so that is simply ignored. Notice that it's not an error, it just doesn't do anything. 3 is already in there. I can discard a value from a set, and then the value is gone. As an alternative, I can remove a value from the set. So let me remove the 9. It appears at this level of discussion, the discard and remove are more or less the same. The distinction is that discard will not fail if the value you're trying to get rid of doesn't actually exist. So, all right, so here's my set S, from which the 3 and the 9 have been removed. If I say s.discard 19, well, there is no 19 in the set, but discard doesn't complain. Remove, on the other hand, does complain, and I get an error from that. So the distinction between the two is, do you want attempts to get rid of values to not be treated as errors or to be treated as errors? That determines whether you use the discard function or the remove function. You can pop a value from a set. Let me redisplay S. Now, because a set is not ordered, you don't know what value you're going to get when you say s.pop. Well, it appears there that I got the first one, but that's just happenstance. If I say s.pop again, well, once again, it appears that I got the first one, but again, that's just luck. The definition of the set is that items within the set are unordered. But the specific behavior of a specific set on your machine using your Python shell may appear to be ordered. All right, it's just that you can't count on a set being ordered. If you start counting on a set being ordered, at some point the set is going to become unordered, and your code will break. All right, we can get rid of everything in the set by doing a clear, which I won't do, and I've already shown you that you can determine whether a particular value exists in the set or not. Okay. Now, so these named operations on slide 21 involved manipulating particular values stored in the set. There's also a whole collection of named methods for doing comparisons of two different sets. And to illustrate these, let me create the two sets shown here on slide 25. So S we will redefine as 35679, 35679, and I'm going to define S2 as 348910, 348910. Okay. So, one obvious thing I can do with sets, mathematically, is I can define the union of two sets. And so I can do that in Python code. I can say s.union S2, and that will give me back a set that contains all of the values that are either in S or in S2, or both. All right, 3, 4, 5, 6, 7, 8, 9, 10. Difference, on the other hand, S dot difference with S2 means to compare S with each value contained in S2, any value that exists within S2 that is also found within S should be removed. All right, so 3 is found in S2, so S difference S2 is not going to include the 3. 5 is not found in S2. 6 is not found in S2. 7 is not found in S2. 9 is found in S2. So the upshot is that S dot difference of S2 is going to be these 3 values, 5, 6, and 7, that are not found in S2. Now, union is a so-called commutative operation. That is, S dot union of S2 is identical to S2 dot union of S. All right, if I say S dot union S2, I'm just creating the union of S and S2. And that's going to be the same as creating the union of S2 and S. So these two things are equal to each other. But S dot difference S2 is very different from S2 dot difference of S. Because now we're starting with S2 and we're taking away any values that we find in S. All right, so we're taking away the 3, we're taking away the 9, and the values that we have left from S2 are 4, 8, and 10. All right, so S dot difference of S2 was the values in S that are not in S2, 5, 6, and 7. S2 dot difference S is the values in S2 that are not in S. And I said that was 4, 8, and 10. Notice, at long last, we're seeing a set that is not shown in a typical kind of ascending order. You know, why is this not shown ordered, whereas everything up to this point was shown ordered? Who knows? You just can't count on the ordering of any set. S dot intersection of S2 is going to be all of the values that are in both. So S dot intersection of S2, let's see, that's going to be 3. Whoops, come back here. That's going to be 3 exists in both, 9 exists in both. So those are the only 2 values in the intersection. And here again, who knows why, these came out not ordered, okay? We got the 9 before the 3 for some unknown reason. You can use symbolic operator symbols for some of these named operations. Set difference, intersection, union, and also symmetric difference. Let me talk about these. All right, so we already did S dot difference of S2. And we saw that 5, 6, and 7 exist in S but do not exist in S2. As an abbreviation, I can ask for S minus S2, and I get the same result. We saw that S dot intersection with S2 is the set of all values that are common to both. Here again, we can say S and S2 as a shorthand. This ampersand symbol in the Java, C, and C++ languages is what's called the bitwise and it gives you all of the values that are 1 in the left-hand thing and also 1 in the right-hand thing. In the case of sets, we're getting all of the values that are common to the two sets, which again is 9 and 3. Vertical bar is union. S vertical bar, S2 is the union. I guess that went off the top, but let me just redo it. Okay. And then finally, the caret symbol in binary mathematics on integers is called the exclusive OR operation, which gives you all of the bits that differ between the two operands. All right, so here's S, here's S2, and if I ask for S exclusive ORed with S2, what I will get is all of the values that are either in S or in S2, but not in both. All right, so I will not get the 3 because that 3 is in both. I will get 5, 6, 7 because those are not in both. I will get 4, 8, and 10 because those are not in both, but I will not get the 9. All right, so I will get 5, 6, 7, 4, 8, 10 in some order. All right, 5, 6, 7, 4, 8, 10. And they happen to have been displayed here in ascending order. Who knows why? Now, there is a restriction on the kind of values that you can put into a set. A set can only contain what are called hashable items. And we don't know enough Python yet for me to be able to describe in complete technical detail what hashable means. So it's easier to just give you a collection of things that are hashable and that therefore you are allowed to put in a set. All of the low-level data types, int values, float values, bool, stir, and none, any of those kinds of values are hashable and can be put into a set. It turns out that a tuple is also hashable if each one of the items in the tuple is hashable. What does that mean? Well, if you have a tuple that only contains some combination of ints, floats, bools, stirs, and none, then that tuple is considered to be hashable. But if you have a tuple that contains, let's say, a list, well, the list inside the tuple is not hashable. Why is that? Because a list is mutable, and you can change the contents of stuff that's in a list. Therefore, a list does not have a fixed size and a fixed collection of values. It is therefore eliminated from the collection of things that are referred to as hashable. Likewise, sets are not hashable. So, here I'm creating the set S3, and in here I'm putting an int, and a float, and none, and a stir, and a bool, and a tuple that also contains hashable things, 3, 9, and 14. Okay, so I have a set now of these 6 items: int, float, none, stir, bool, tuple. And each of the items within the tuple is also hashable. So this all is fine. Here you see why the very notion of the ordering of things in a set is ridiculous, because you can't define an ordering between a string and a tuple, for example, or between an int and a string. When I display S3, it just comes out in some arbitrary order. Who knows why? And if you did a definition of the same set and you displayed your S3, yours might very well come out in a different order from what I'm getting in my shell. All right, so we've got lists, tuples, sets, and the fourth built-in collection time is dictionaries, dict. A dictionary is also defined using curly braces, and a dictionary consists of key value pairs separated from each other with a colon. So here I'm defining a dictionary called N2E. I often use names like this for my dictionaries because the idea is that it's a mapping from a user's name to that user's email address. All right, so John is a key here associated with this email address, jkostlin@gmail.com. Then Al is a key associated with al@alcorp.net. Bob is a key associated with the value bob@bsoak.com. And that thing is a dict. I can use a key as an index into a dictionary. Notice I am using the square brackets here. But in the square brackets, I have to use a valid key. I can't use like, well, I was going to say I can't use things like integer subscript 0, 1, 2, 3 unless I set up my dictionary using those integers as key values. All right, so if I had used 0, 1, 2, 3 as keys, then I could certainly use those as keys. New items are easy to add. Let me just hammer in my original N to E dictionary. Okay, so John is associated with jkostlund@gmail.com. Al was, I think, al at alcorp.net. And Bob is the key associated with Bob at bassociates.com. All right, if I want to add a new value, a new item, I can say N to E and give the key for this new item, psi, let's say, with a value assigned for that key, psi at nou.edu. And now N to E has had that fourth item added. Okay, there are named operations you can use with dictionaries. I'm going to just run past those. And let's take a look at the iterables that you can use to interact with all the stuff that's contained within the dictionary. So here's my dictionary, N to E. If I do a loop on the keys, all right, there are three different ways that I can iterate through the items contained within a dictionary. I can either iterate through the keys and print out each key, and let me have the end of the line be set to a space so that everything comes out on one line. Or I can loop through the values. Okay, so these are the email addresses. Now, if I loop through the items, each item consists of both a key and a value. This information is presented to me as tuples, all right? So for each item, I don't get something like John : jkostlin@gmail.com. What I get instead is a tuple containing John, jkostlin@gmail.com. Okay, so here are the item values. Okay. All right, so that takes care of dictionaries very hastily, as I said, and we have now discussed the low-level data types, int, float, stir, bool, and none, and we have talked about the built-in collection types, list, tuple, set, and dictionary. We can do conversions among data types by using the data type name as a conversion function. And I'm not going to go through each one of these. We've just got to zoom along here. So I can convert none to a string. I can convert a float to a string. I can convert floating point values and booleans and strings representing integers. I can convert all those to ints. I can convert integers to floats, strings to floats. Now, Boolean is an interesting case because it turns out that any value of 0 or empty is treated as false. So 0 is false, 0.0 is false, an empty string is false, but any numerical value other than 0 is true, and any string other than the empty string is also considered to be true. A statement in Python has to be contained on a single so-called logical lines. Now, a physical line, in contrast, is simply some sequence of characters at the end of which you type a new line. So for short statements, a physical line and a logical line are one and the same thing. If I say x gets 12, this is both a physical line, it is also a logical line, and it is also a correct statement. So it does end up creating a variable called x referring to that integer value 12. But if you have code that's pretty long, Python is very unlike Java, C, C++, in that Python is very concerned about line boundaries. I cannot, in Python, say x gets, and then just hit the enter key and type my value on the next line down. If I attempt to do that, I get told, no, that's invalid syntax. All right? So how do I deal with that? Well, one way I can deal with that is to add the backslash as a continuation character to allow me to specify another physical line continuing the same logical line. So now I can say 12 down here, and that worked. I hope you'll agree with me that that is extremely ugly, using the backslash. It's both ugly and it's also easy to forget. So another way of dealing with this problem of having a hard time splitting a lengthy logical line across several physical lines is any code that you write in parentheses or in square brackets or in curly braces can be spread across multiple lines just fine. So if I were to say this, x gets, open parenthesis, 12, close parenthesis, well, a 12 in parentheses is just a 12. So there I was able to type x gets 12 on, I don't know, 8 lines, 10 lines, whatever it was, and it works just fine. Or if I wanted to find a list that has a whole bunch of values in it, I may only be able to type 10 values on the current line, and then I have to hit the enter key and keep going. Since this is in square brackets, that's fine. I can just type the enter key and keep going, and eventually type my closing square bracket, and now I have my list. Okay, so it's very common for people to use parentheses, in particular, to avoid having to use that ugly backslash to continue statements. Len I have already mentioned. Len will tell you the number of items in any collection. Some of these collections are what are called sequence types, specifically list, tuple, and stir. Now, I have not shown you that a stir can be subscripted, so let me do that. I did show you can ask for the len of a stir. What I did not show you is that you can use a subscript into a stir. So stir1 sub 5, well, what is that? All right, the h is sub 0, 1, 2, 3, 4, 5. Cool. So stir1 sub 5 should be that comma character, and it is. Because lists, tuples, and stirs are sequences, you can use slice notation to request just a portion, a slice, of that collection. Here I've got my old list M, my old tuple T, my string stir1, and if I say M sub, notice that the slice notation has 3 parts. We have a starting position and then a colon, one past a stopping position and a colon, and then also a step size. So if I say, let's start from position sub 1 and go up to but not including position sub 4 with a step size of 1, what does that mean? Well, in M, we're going to start at position sub 1. We're going to go up to, but not including 4. So there's 1, 2, 3. This is position sub 4. And so what I claim is that starting from 1, going up to, but not including 4, with a step size of 1, should give me just the 552 sub, slice from within M. Same idea for T. If I say T sub, this time let me say 0 colon 2. And if I leave out the step size, it defaults to 1. All right, so 0 colon 2 means give me item sub 0, item sub 1, but not item sub 2. And there we go. So now I have a tuple that only includes the slice of the first 2 items from the tuple. You can leave out the first index as well, and that defaults to 0. Or you can leave out the ending index, and that defaults to the length of the sequence. All right, so here's stir1. Let's use it now. If I say stir1 sub colon 5, well, you may remember that stir1 sub 5 is this comma character. So in effect, what I'm asking for here is a slice of stir1 up to but not including the comma. So I just get hello. On the other hand, if I say stir1 starting from position sub 5 and going to the end, okay, going to the end is equivalent to going to, it's a little hard to say, but we're going to go to 1 before the index that's 1 too far. In other words, we're going to go to the last item in the string. And so that's comma world. Now, each slice of a list is a list. And I can use plus to concatenate lists. Each slice of a string is a string. And I can use plus to concatenate strings. So, here's M. If I say, let's take a look at M up to but not including item sum 2. Sorry, let's take a look at M, starting from item sub 2 to the end, and let's append to that M colon 2. This is going to give me back a list that contains all the same values as M, but with the order swapped around. So I'm going to get 520 as the first part of my resulting concatenated list, and 75 is the remaining part. So I should get 52075. Here is the string hello. If I ask for the string hello, now I don't need a variable name to do this slicing on. I can just directly use a literal string and ask for all of the characters up to but not including sub 3. Now what is that? So H is sub 0, 1, 2. Sub 3 is the second L. All right, so I just have HEL. And I can concatenate to that another string, P exclamation mark. All right, so there's a silly trick. So that's what slicing is about. I can also do slicing within tuples. Here I am creating a tuple that only contains a single value by giving the value and a comma after it. So if n currently, let's see, I guess I changed n somewhere along the way. So let me reset n to be what we have here. So it's going to be bald eagle soars. All right, I can say n gets, well, the existing n up to but not including item sub 1. That's item sub 1 would be bald. And then let's concatenate to that this one item tuple, harpy, and then we will concatenate n sub 2 colon. All right, so n sub 0 colon 1 is as a tuple. N sub 2 colon is eagle soars as a tuple. And so the upshot here is that I've got tuple concatenated with tuple, and I end up with a harpy eagle soars as my result. Okay, so now that we've looked at the low-level data types and the collection, the built-in collection types, the next thing we're going to take a look at is the equality, relational, identity, membership, and logical operators, which is a big mouthful. So this includes the equality test and the is not equal to test, the less than, greater than or equal, less than or equal, greater than or equal to comparisons, the is and is not, those compare to see whether two objects are the same object or different objects, and the in and not in, which test whether a certain value is in a collection or not in a collection. Those are all intended to be on the same line because they all have the same level of precedence. So those are the highest precedence operators that we have in this table. Then, in addition to those, we have three logical operators, not, and or, which are lower in precedence. Not is next lower, and then and is lower than not, and or is lower than all of these other things. We can use parentheses for grouping all of these comparison operations and logical operations, just as we can use parentheses for arithmetic operations. So the is and is not comparisons compare so-called object IDs to see, for example, whether two variables refer to the same object or not. The in and not in are testing whether a certain value exists as a member in a certain collection, a string, a list, a tuple, a set, or a dictionary. And then the is equal to and is not equal to are comparing values of objects. Now, I showed you one example of the print function already. Here's just another example. In a program, you need to use the print function to display output for the user to read. In the shell, as we know, we can just type the name of a variable and we will see the value of that variable if that variable exists. But the print function, okay, stir1, s1, not defined. I was hoping I could find the variable that referred to that 4-line string. You may recall that we printed that 4-line string, and each place where a new line character occurred, we did get a line break for the next line of output. The print function is able to display multiple values. Here we're displaying the value of the variable a, which turns out to be a string. And then the string literal, Bob, the value of the result of computing 11/3 and true. And so here is the output that we get. You separate the different arguments from each other in the print function call with commas. You always separate arguments from each other in a function call by using commas. And by default, the print function will display spaces between each of its arguments. Whoops, highlighted too much there, so just that space. But it turns out that you can use something called the sep keyword argument to modify the separation that's displayed between the values in the print function call. For example, here I've defined sep to be a comma, and consequently, instead of spaces between the values, I'm getting commas between the values in this print function call. This is both a specific example for the print function. It's also a general example of the idea of keyword arguments. Many functions accept these so-called keyword arguments. If you need to make some kind of decision, remember that Python provides this if, elif, else kind of statement hierarchy. If you want to make a decision using if, elif, else, you do have to have exactly one if part at the beginning. The idea is if the Boolean expression following the if is true, then the sequence of statements contained within the if are executed. Following the if, we can have 0 or more elif parts. We don't have to have any, but we can have as many as we want. And here we say elif, and then again, there's some Boolean expression. If the topmost Boolean expression is false, but this elif Boolean expression is true, we perform the statements associated with that elif. And then that can, there can be a chain of as many of those as you want. At the bottom, optionally, you can have exactly one else part, or you can leave out the else. One form of loop is what's called the while loop. The while loop, if you've done some Python programming and ever used a while loop, you will remember how it works. I'm not going to bother going into that. A much more commonly used loop is the for loop that steps through each item in some kind of iterable and allows you to make use of that item's value. Now, all of the collection types that we've discussed, lists, tuples, sets, and dictionaries, are iterable. And so all of those can be stepped through using a for loop. Similarly, a string is an iterable, and we can step through each of the character values within that string using a for loop. All right, so in this first example for loop, the variable I is going to be set one value at a time to first the value 1, and then 5, and then 9, and minus 4 and 12. And we're going to print out the squares of those values on separate lines. For this next for loop, we're printing out H on a line by itself, and then E, and then L again, and then O. There's a function called range that can also be used as an iterable. It is an iterable that can be used in a for loop. And it can be used with either 1 or 2 or 3 arguments. If you specify one argument, then what you get from the range is all of the integer values from 0 up to 1 less than n. All right, 0, 1, 2, blah, 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 n minus 1. If you specify 2 arguments, then the first argument is the initial value, and the second argument is one past the final value. With 3 arguments, we've got the initial value, one past the final value, as well as a step size, which, if you leave it out, the step size is 1 by default. Here's a couple of examples of using a range. If I say for I in range 5, print I, let me also specify that my sep is, my end of line. By default, the end of line is the new line character, but I want to remain on the same current line, so I'm going to modify my end to a space, and that enables me to print each of those values in that range on the same line. Here I'm using a negative step size because I want to count downward. I'm starting from 4. I am ending just before I get to minus 1. And I'm counting in step sizes of minus 1. So this is going to be like a countdown. 4, 3, 2, 1, 0. 0 will be the last value I get, because if I subtract minus 1 from 0, that will get me to minus 1, which is too far. Okay, so for I in range, let's do 10, minus 1, minus 1, print I, and again, let's have all of these be on the same line, just separated by spaces. And so there's a countdown to 0. Python often puts a collection of related functions, and sometimes variables, and sometimes class definitions, and so on, together into a single file called a module. You can make use of the facilities contained in a module by importing that module in your code. For example, the math module contains many commonly used mathematical functions that are not directly built into Python itself. For example, there is a square root math function that we might use. Square root of 4 should be 2, but we get told that square root is not defined. We can ask for e to the 10th power. Okay, so this is e to the 10th power. And that function is not available automatically. But if we import the math function, the math module, excuse me, and even better yet, if I say import math as m, so I can use m as an abbreviation, now I can access these functions. So m dot square root of 4 is 2.0. M dot exp of 10 is e to the 10th power. M dot log of 1 is the natural log of 1, which is 0. M dot cosine of 0 should be 1. And on and on. So there are a number of functions in the math module, and you can look those up in the documentation. All right, well, I had hoped to make it through NumPy, but we have already burned up a little more than an hour and 20 minutes, so I'm going to have to pause here, and we will look at NumPy and hopefully a large chunk of Python, a large chunk of pandas on during our second lecture. All right, take care.